In the last lecture, we talked all about the encoder process and the difference with the encoder between the transformers architecture and the hyperdimensional computing architecture. In this lecture, we'll talk about the decoder and that same exact difference. So, starting off with an overview of the transformers-based decoder. The purpose of the decoder within the transformers architecture is that it generates output sequences using encoded information and previously generated tokens. It is exactly as people describe it, a next token predictor. It predicts the next token in a sequence. What's important to note within that, though, is that depending on the embedding process and how you embed those tokens, the tokens can represent different things. They can represent usually about like 4 letters is what a token, a typical token can represent, but a token can represent a whole sentence, and more data, right? So I'm just trying to let you understand that there are deviations of what a token does and what a token can represent, but inherently a transformer architecture is always predicting the next token in a sequence. Whatever the token represents, it's trying to predict that next token. How it does that is it utilizes these processes that we've talked about a lot and a little bit in the previous lecture, which is this process of feed forward and then backpropagation. And then so essentially you feed the input through the model. The model is then told whether it's right or wrong on that answer. And then that right or wrong answer, that feedback is then backpropagated through the model. And then essentially that's how the model learns, and that's how the embedding process works. And then so within the actual encoding or decoding process, what happens is within transformers, you have the attention mechanism that everyone is fully aware of. Like attention is all you need, right? And then so that attention mechanism, what it's doing is it's doing that decoding process within the transformers mechanism. And then so remember, the transformer is always decoding the next token. So it's always, that process stays the same, but again, what a token represents can change. And a token can represent the whole sentence. It can represent the whole corpus, meaning the whole entire data set. And then how that varies and how it looks through and what it knows to focus on within that is the attention mechanism. And that's where the attention mechanism comes into play. And that's why you need to fine-tune and train these models as an encoder and decoder sequence. And then so, and when we go into the code here, we have a very simplistic coding example of an encoder or of a decoder. And what makes this code that we're looking at very simplistic is the fact that we're utilizing this pre-trained decoder. In this instance, we're utilizing GPT-2 as our decoder instance, as our decoder model, right? And then so this instance of GPT-2 has already been trained on embeddings. So it's already entrained as an encoder, and then we're utilizing whatever embeddings it has for these instances in our data set. In this instance, the cat sat on the mat and we want to take its existing beddings and represent and decode those existing beddings. And then so again, this is always, it's probabilistic as to the decoding process, which is why we need a pre-trained decoder that can give us some sort of logical reasoning like that makes it non-probabilistic with regards towards the decoding process. And that's what this GPT-2 model does here for us. And then we can essentially adjust some of the parameters within this. Again, there's always a probabilistic aspect within this, and then we get our decoding of our tokens. And then our decoding of our tokens would look very straightforward and very simplistic. It's going to take this a minute or so to run, but it'll just be a sequence, like an output sequence of numbers, of tokens, right? Like an array. As opposed to looking at the hyperdimensional computing model, so the HDC decoder, whereas in this instance, the purpose of this decoder is that it recovers or interprets the encoded information, the hypervectors, by comparing them to a reference set of known hypervectors. So it's comparing, again, that dictionary. From the building on that previous lecture, when you're encoding the dictionary. So if we had a dictionary, a literal dictionary of data, and then we have our encoding in this instance of cat, mat, sat on the, we would be appending this to our dictionary. And then the big thing to note within that, right, and to formalize this concept and to make it very simplistic and very straightforward. So let's say that we are taking our existing HDC network, our existing encoder, decoder, and it's been trained on the dictionary. And then so whatever that is represented as a shape with this, the relationships already built into the model, right? So the model in that instance would have, as if we took cat, some sort of relationships for cat, such as like feline, nocturnal, predator, etc. Right? Examples that I typically use for cat, and then it would already have those embeddings within it. And then so what we're doing is we're just, and the shape off of all of that data. And then so when we add these new embeddings, we're adding more kind of like strings that would go, more connections. And then we're changing the overall shape of this data set overall. And then so those two things in conjunction are what we do when we go through this process. And then so it's a different process overall, right? This is doing similarity matching as well as probabilistic interpretation. Whereas with this, it was doing probabilistic embedding and deterministic. It's always the deterministic decoding. Right? We can, like, within what we're doing with the GPT-2 model here, why we can use the GPT-2 encoder or decoder is because we get a deterministic output, right? Hopefully, whereas in this instance, we're not actually getting what we would want. The model is giving us a continuation of the output here. And it looks like because it was a padding sequence error, which I'll fix by the end of this video. But what I want to showcase within this is, so you saw that whole time, and there's a very simple reason I wanted to run this, right? 2 minutes to run. And then so this is, again, because we have to load the this pre-trained model. We're loading this GPT-2 model, which has been pre-trained as our decoder in this instance. And if we didn't have it pre-trained as a decoder, it wouldn't know what to do. If we just threw it some embeddings, and then even if we took a GPT-2 model and then we had it spit out some embeddings, and then we took a different GPT-2 model that wasn't trained as a decoder, and then we said, hey, here's the embedding sequence from the embeddings from this GPT-2 model, and whatever they are for the cat set on the mat, the array for that, and then we gave it to the GPT-2 model. The GPT-2 model would look at it just as you would be like, I don't know what to do with it, because it's not trained on it. And then so that's the big bottom line that I want to highlight within this. So we have to train it, and then that attention mechanism. And then while these things are cool, and then we talk about these concepts and within this, what that does is it adds computational complexity. It's the bottom line, right? It just took 2 minutes just to set this up and give you a simple illustration of running a decoder for the cat set on the mat for that one sentence, as opposed to in hyperdimensional computing, the same type of thing. I hit here, it's 0 seconds, right? So 2 minutes compared to 0 seconds. And then it's because I don't have to go through that same type of process. So again, it's going to do a probabilistic decoding process. So it's just going to make stuff up if it doesn't have stuff in there, which is what it's doing in this instance, right? And then so that's why it took 0 seconds. It's because it doesn't have any reference information in here, and it's just making up these values. But you can see the speed of it, and the speed of it is because it has 0 data within it, right? And then so this is the computational drawback within this, right? If we compare this compared to this with 0 data in it, we just saw it. It's 2 minutes compared to 0, like literally 0 seconds. But as we put more data into this, that computational time increases from 0 seconds. And it's not good, like, I mean, 2 minutes is a lot, right? If I put the dictionary in here, like the literal dictionary, we might be talking about, and we had it computed and already embedded, maybe that would increase it to 45 seconds. So we'd be looking like an actual comparison, a real comparison would be like more like maybe like say a 45-second comparison as opposed to the 2-minute comparison that we're looking at here, which would be speedy, right? But as you get more and more complex, like more complex than a dictionary itself, like and more data sets, there is a point and a threshold where this becomes more computationally expensive than this. It's big, but there is a threshold that you can cross where you get into a point where like this method is no longer as computationally efficient. And then so as a kind of short overview, combining these processes overall, right? Looking at the encoder and decoder as a full entire sequence. If we look at transformers and exactly what is going on within that encoding process, very simplistically starting off with the input tokenization, the input text is split into individual tokens and then it's converted into its numeric IDs. These embeddings are then mapped to dense vectors via learned embeddings, and it utilizes positional encoding, which adds positional information to the embeddings for sequence awareness, and it utilizes that self-attention mechanism that it needs built in to calculate the relationships between all of the tokens, which is why that attention mechanism comes in, to generate the attention score, which generates a context awareness representation, and it uses feed-forward layers and refines the token representations layer by layer. So within that, you're introducing probabilistic elements from jump, right? You're not utilizing linear algebra within this input tokenization process. You're already jumping to calculus. And then with the for the decoder, it takes the encoder outputs and the previously generated tokens. It uses a masked self-attention mechanism, which just hides the token. And then it computes relationships among already generated tokens while masking the future tokens to maintain autoregressive behavior. The encoder decoder attention mechanism. So the attention mechanism is responsible for both encoding and decoding, incorporates the context from the encoder and outputs that into the generated sequence via the feed forward layers, which refine and transform the predictions, which gets your output generation. And it produces the output based off of the next token via softmax, which is that backpropagation, and then it repeats this sequence over and over and over again. And then that's essentially what's going on internally within this model, and that's your embedding and your encoding and your decoding process within the transformers model. That whole entire sequence, again, it's computationally expensive, right? Especially for just a simple sentence like the cat sat on the mat. Less computationally expensive if you have a bigger data set and you're spinning it up and it's already spun up, then you're just going through, right? Which is kind of how it works overall, but highlighting that. And then so within this, what does that look like within code? We have it here. We spin it up. Again, it's going to take 2 minutes to load even this simple model, and this is a simple T5 model to load. And then this would be essentially we have to load the model, create our input sequence. So we have our input sentence of the cat sat on the mat. We have to encode that, create the embeddings for it. We do that, create the embeddings, train the model on what the embeddings are so that it can decode the embeddings and then go from there. And then within this decoding process, I should highlight that the math does get simpler, right? This is linear algebra as opposed to calculus up here, right? So it starts off very hard as far as the math and very complex, very random as far as the math. And then this process is very deterministic and very straightforward as to what it's doing here by the time we get here. So up here, up at the top, we have some randomization and some probability in the process. And then down here, it's all linear algebra by the time we get to the end. Whereas with hyperdimensional computing, pointing that out because it's the exact opposite, right? So starting off with hyperdimensional computing and the token representation, each unique token is assigned a hyperdimensional binary vector or a hypervector, which is randomly initialized. So the initialization sequence is randomized. That's the only randomized part of this, right? And that's like kind of like. The way that I look at it is you're creating a box and you're booting up a box, right? And then the model needs to know upfront what the dimensions of the box are. But I mean, you're creating an imaginary box out of thin air, so they can literally be anything, but you need to define them for the model to base it off of something. And then so you're just, here's some random dimensions. Here's literally random dimensions. Go at it, right? And then so from there, then the process is binding and bundling is all that you're doing within this, right? So it's linear algebra. Binding is relationships between features or tokens that are encoded using operations like element-wise multiplication, and bundling, which is utilizing multiple token hypervectors that are aggregated, they're summed together. So again, linear algebra into a singular hypervector to represent the whole input. So it binds, it uses linear algebra to add the plus cat plus mat plus sat, and then it bundles all of that together. And then so the plus cat plus sat plus on plus etc., and that full sequence as one full sequence is one bundle, right? And then so binding to get there, and then bundling to get the end result. And then within the decoding process is that's where you introduce the calculus and the probability within this similarity matching. So when you want to decode, you take the encoded hypervectors and you compare them against a reference set of hypervectors utilizing the cosine function, utilizing cosine similarity, and dot product. So you utilize cosine similarity and dot product within transformers as well, but that math occurs during the backpropagation process, and you're just including that within backpropagation. Whereas here, again, there's no backpropagation, no gradient descent, so you do this process during the decoding process instead. And then so this cosine similarity still occurs within there, it's just in the decoder. And then like this most simplistic way, let's take our example of cat, right? And then let's assume that the most similar hypervector to cat would be feline. And then maybe after that, it would be kitten. Because that, yeah, and then, like more, you go more and more distance out from the word cat, but how it's decoding is it needs something to compare it to. So cat in comparison to feline, cat in comparison to dog, etc. Right? And then it's doing these comparisons based off of these these vector comparisons is what it's doing, right? And then so the encoding is deterministic, but that compared to feline, I mean, that's what I just made up. So that's probabilistic. And then maybe the model probabilistically chooses something else. Maybe it says, hey, feline isn't the closest. Maybe kitten is closer than feline, etc. Right? And then so that's where that probabilistic element comes into it. And then so what does this look like in code? The code looks very similar, right? Because again, we're not like within this, we're loading the pre-trained model and then these pre-trained tokenizers. In this instance, the T5 model. Whereas in this instance, we're not loading any model, so we're not doing any training in this instance, and no training had to occur. We're just flat out rag tuning on the cat sat on the mat, and then we feed it, and then we get our output within this, and then we can run it and then get our hyperdimensional encodings. And then in this instance, again, just showcasing to you like rapidly how quick this is, right? I'm not running this because it's going to take 2 minutes to run and execute this, as opposed to literally 0 seconds again. You can see we're adding a little bit of complexity, and we're adding stuff to this database. We're adding information to this, and then with this information that we've added, it's still at 0 seconds, right? Like, it's still, it takes a lot before the computational complexity of this model is worse than this model, which is why people look towards hyperdimensional computing. And so overall, wrapping this up, this gives you the summarization of the biggest difference between HDC architecture and transformers architecture. And then so if you're big into like graph neural networks, this essentially creates like a living graph neural network for you, a growing graph neural network, and the model itself is a graph neural network. It's kind of like how I frame it in my head, so I can see why a lot of people are interested in learning more about this architecture, and I can see why there's not a lot out on this architecture, right? Because it is kind of hard to break down this process. Hopefully I've done a good job of that for you. If you like this type of content, please like and subscribe. Thank you very much.